All right, y'all ready to knock this lesson out? So what we have left to do is the analysis part. So we're talking about series circuits. We decided that was one path for current flow, components connected end to end. With one path for current, we had one current. Current was the same. Current is equal everywhere. And then the voltage, the total applied voltage is divided among the individual components proportionally, and the individual voltage drops add up to equal that total voltage. Matter of fact, series circuits are called voltage dividers. So anyway, I put the formulas up on the board. Basically what we're looking at what we already know. The total resistance is equal to all the resistors added together. That the total current now is from here on out. Actually, from here on out, it's pretty much straight up Ohm's law. Because if I look at this, it's telling me if I want to find the total current, after I found my total resistance, if I want to find my total current, I take my total voltage and divide it by my total resistance. So the voltage applied to the circuit divided by my total resistance is going to give me my total current. And what do we know about current in a series circuit? Well, current in a series circuit is the same. That's the mathematical way of saying the same. It's equal everywhere. So once I know all my currents and my resistor values are given in the circuit, all I need to do is take the current through that resistor times that resistor to get the voltage across that resistor. Now, this is the thing about Ohm's law. You got to use apples with apples and oranges with oranges. In other words, if I want to find total current, well, I got to use total voltage and total resistance. If I want to find the voltage across resistor number one, I got to use the current through number one times the resistance of number one. I can't find the voltage for number two by taking the total resistance and multiplying it times the current of R1. Well, in this case, I could, or R1, all currents are the same, but you follow what I say. That's the thing about Ohm's law. If I want something for one, I got to use all ones. If I want something for twos, I got to use all twos. If I got totals, everything has to be a total. That's the thing about the Ohm's law formula. But then it's all just pretty much Ohm's law. I'm finding voltages, and then when I'm done, I found all my voltages. Now I can turn around and add those voltages up to see if it's equal to that total voltage. And it should be, because it divides that total voltage up. And here's the other deal. Now, if its total voltage is 10 volts and you add it up and you get 9.998, hey, that's 10 volts. That's a calculator rounding thing. That's the difference between me storing the number in my calculator and you clearing the calculator out and entering that number back in. Because the calculator actually stores all decimal points behind it. Well, when you clear your calculator out and re-enter it, you're only entering in 3 decimal points behind that decimal. That's going to throw a little bit of error into the calculation. That's fine. That's fine, because the meter itself and the tolerance of the components is going to throw your actual measured value off more than any little bit of calculator rounding. Don't worry about if it's 10 and I come up with 10.001 or 10.002. Look, that's all the same. So don't worry about the small stuff. All right. So copy that real quick. Make sure you have it. I'm fixing. You better pause it because I'm fixing to get started. All right, solve this one. So what I need you to do is pause it because I'm fixing to solve it. So solve it and then get it started back again. All right, so first of all, total voltage is given, right? Total voltage is given. To find total resistance, I added 1.3K, 5.6K, and 4.7 kilo ohms. That gave me 11.6 kilo ohms. I turned around, used Ohm's law, found total current by taking my total voltage divided by my total resistance and got my total current, because I know current is the same in series, one path, one flow. Current's the same in series, all my currents are the same. So I took that current and I multiplied it times R1 to get the voltage of R1 in millivolts. Not every milli is an amp. If I'm looking for volts, you better put volts. -3 is millivolts. Multiply my current times the 5.6K, I get 3.138 volts, and then times the 4.7K, I get to 2.634 volts. Just to check, I add them all up, and sure enough, come up to the 6.5 volts. All right, so let's do another one. All right, do it real quick. Pause it because I'm fixing to do it again. All right, did the same thing. Added them up, got my total resistance, took my total voltage, 20 volts, divided by my 5.1K, gave me the total current flow, which I knew is the same, 3.922 milliamps, and then I took that and multiplied it times each individual resistance to get my individual voltages. And when I add this back up, nope, that don't come out right. Let's see here. Pooh. Now, ain't that something? And that's on film too, huh, folks? So I just seen if you were paying attention. Oh, that sucks. All right. See, what the deal is my calculator is solar powered, and the lights in here are not. I'm blaming on something. All right, so here we go again. So that'd be just one more time: 560 plus 2.7 EE3 plus 1.2 EE3 equals, okay, 4.46 kilo ohms. Sound better? All right. Give you 4.484 milliamps. Now, there you go. So look, there's one other problem on this worksheet that you're fixing to do. You know, check these out. T. Check these out on the worksheet. There's one other problem on that worksheet though, that's like this. this is what you got. Now, you can't go the conventional way of finding and analyzing a circuit. You'll notice that there is no resistance value given for resistor number 1. However, there is a voltage value given for number 2. Now, you got to see a correlation here. Well, I don't have a resistor, but I got this voltage. This voltage has got to mean something. So what can I do with the voltage? Well, it's a voltage across resistor number 2. Hey, I got the resistance for resistor number 2. If the voltage for number 2 divided by the resistance of number 2 will give me the current for number 2, well then, hot dog, I have figured out all my currents. So let's try that. I got the 7.6 volts. I'm going to take that 7.6 volts, and I'm going to divide it by that 1.2 kilo ohms. Okay, and this is an important calculation, and the way my luck's been going, I'm going to go ahead and do it twice. So the 7.6 divided by the 1.2 kilo ohms, that gives me 6.333 milliamps. All right, so I'm going to store that in my calculator. If you clear it out, your answers might be a little different, but don't worry about it. So that's 6.33, but you got to understand. That's 6.333 milliamps for resistor number 2. That's all I solved for just then. But now I know that current is the same. So, all right, so that gives me all my currents. What am I going to do now? Well, I got the current total. I got the voltage total. All it says all I need is 2 to find the third. So guess what I'm going to do? I'm going to find total resistance. So I got my current there, and I'm going to divide my 15 volts by it. So it gives me 2.368 kilo ohms. 2.368 kilo ohms. All right, I got 2.368 kilo ohms. Let's see, I got the current for number 3. I got the resistance for number 3. Current and resistance, I can find the voltage for number 3. So let's take that current, multiply it times the resistance for number 3. That gives me 3.04 volts. 3.04 volts. So here I am. All right, I got everything except for the voltage across 1, and I don't have the resistance for number 1. What am I going to do? Well, I got the current, but I can't do poop with that. However, I got to be thinking. What did I say about all these voltages? Well, I said that these voltages should all add up to be equal to that total applied voltage. Remember, if I go down the street and I stop at this store and spend $3.04, stop at this one and spend $7.60, and I left the house with $15, how much do I have left to spend there? It's that simple, but you got to understand it. So what am I going to do? Well, I'm going to take that 15 volts and I'm going to subtract out that 7.6, and then I'm going to subtract out the 3.04, and that leaves me 4.36 volts across resistor number 1. So that 4.36 volts across number 1. Now, how do I find the resistance of number 1? I could do it a couple of ways too, because I know these resistances all added up equal total resistance, so I could do it the same way with the voltage. But heck, I got the voltage in my calculator. I got the current stored up, so the voltage divided by the current will give me the resistance. So I'm going to take that voltage there and I'm going to divide it by the current. Recall 1. And that gives me a resistance value of 688.421 ohms. All right. So what did I do? Well, the first thing I did, I had the voltage of R2. I divided it by the resistance R2 and got my current. Since I got my current total, I took my voltage, divided by that current, and got the resistance. I had the current for 3, so I multiplied it and got the voltage for 3. I took the two voltages, R2 and VR3, subtracted them from the 15 to leave me the 4.36, which I turn around, used Ohm's law, divided it by the 6.333 milliamps. Voltage divided by current gives me resistance, and came up with the resistance value. Now you can check it by adding up all your resistances. So that value plus the 1.2K plus the 480 equals 2.368 kilo ohms. Chicka-pow. All right, so go do your worksheet. You may want to look at this video tail end here, but I'm trying to keep it short and sweet. All right, folks, I'll see you when we see you. But if you need something, call me, let me know. All right? I just want to do something like that.